I've always loved planning a party and the anticipation while waiting for the day to arrive.
When I was a child, I always wanted to have a birthday party on the moon. Maybe a lunar picnic, or even better, eating blue string pudding with the clangers. It's just a wonderful way to celebrate the passing of time. Another journey around our local star, the sun.
Tonight, some fabulous guests are gathered to celebrate something very special indeed.
There's not a person, it's a place. A place known as the home of time. A place that has been instrumental in creating the world around us today. Join me in celebrating the 350th anniversary of the Royal Observatory, Greenwich.
Welcome to the Sky Night.
I'm standing now on famous ground. On either side of this line, I can go from the east to the western hemisphere and back again in an instant. It's like the equator, but dividing west from east, not north from south. It extends that way, north through the UK, and that way south through Spain and France, West Africa, all the way down to Antarctica. It's called the Prime Meridian. But why is it here? In 1675, King Charles II issued a royal warrant for the building of an observatory and picked a man called John Flamsteed to be his Astronomer Royal. The need was grave. The difference between life and death for those at sea. The Navy required accurate star positions to improve navigation and reduce the number of shipwrecks. A single reference point was needed for people to work from, a point on the map to mark 0 degrees. And as years passed and global trade increased, there was a need for a reference point in time as well. And it was thanks to work done just there that the world chose Greenwich to be that reference point. Night by night, the Astronomer Royal would track the Earth's rotation, watching stars arc overhead as they crossed a favoured north-south reference line, a meridian. But it was this instrument, the airy transit circle, and the meridian which it defines that became the one we now know as Prime. George Biddleary, the 7th Astronomer Royal, spent nights down in this pit, looking through this telescope, recording the position of stars as they passed through the crosshairs of his telescope, marked with the finest spider silk. The star positions were published in the Nautical Almanac, a reference book carried on every ship in the Royal Navy and countless others around the world. Sailors could consult the almanac and calculate their vessel's location using the relative positions of the stars and the moon. This was vintage GPS, all done without a computer and far from home. The reach and reputation of the formidable British fleet was founded on astronomical observations made right here, and so the world's prime meridian was born.
Given their unsocial hours, it made sense for Astronomers Royal both to work and live right here at the observatory. That included hosting dinner parties for the greatest thinkers of the moment, to come together and share their ideas about the universe. Tonight, the topic of discussion is time.
Oh, good evening, everyone.
Good evening.
Thank you so much for coming out here.
Thanks for the invitation.
Yeah, delighted to be here.
The observatory is celebrating 350 years, but was this building around at that time, and what was it used for?
The building we know as Flamsteed House was built at the very beginning of the observatory. So Christopher Wren had a great phrase when he was describing the building. He said it was built for the observer's habitation, so that is the place where John Flamsteed and his family were going to live, but also, he said, and a little for pomp, which is showing off. And this was the King's Observatory, after all. So, gateway to the stars on the
top
hill.
of the hill.
Yeah,
It's elevated already.
It was an interesting time. You mentioned Christopher Wren, it's Flamsteed, you had Newton, and there was that group that formed the Royal Society.
Yes.
We think about the big inventions in science at that time with the telescope and the microscope, but of course the clock as well. For accurate timekeeping, you couldn't do science without it.
Yeah. So, yeah, I mean, right up until the 19th century, people are still using their local time, which for most purposes will be the sundial.
In Oxford, there's a joke that we still use our local time. All the students are 5 minutes late for their lectures, so it's still running on Oxford time, which is 5 minutes behind Greenwich, so...
Yeah.
Trains had replaced the horse and cart, ushering in a standardisation of time across Britain. Visual signals like the Greenwich time ball existed already, but a new public demand for precision timekeeping was growing.
George Airy, as Astronomer Royal, was issuing signals by telegraph for people who wanted to subscribe to a time service. And, banks, things like, legal, houses of
when
Parliament.
the contract's signed and things like that.
Absolutely, yeah. It could be really crucial in terms of a court case. When did something actually happen? But there was also an alternative, slightly sort of cheaper service that went along. There was one of the assistants here called John Henry Belleville, who made a little, with permission, made a little extra money on the side by taking a chronometer, a very accurate clock, and would then take that into London and take it around to particularly chronometer makers, so people who themselves were creating precision instruments and really needed to know what the time was. What was interesting is even after we had the wireless signals, even after you start having town clocks that are more accurate, you have these chronometer making businesses want the personal service. And the business, after John Henry Belleville died, was taken over by his widow. She continued the role, and then their daughter as well, Ruth Belleville, right into the 20th century. Something like 100 years of that family carrying out this business.
I'm late for nearly everything. If I almost had to sort of subscribe to a time, I don't think I'd bother. Because I think it's the ideal excuse. I wasn't too sure what time was. Just keep it general.
I'm the opposite.
Really?
I'm quite obsessive about knowing the time. And I think, because I obviously observe quite a lot, you need to have the precision of timing and whatever to know when you're going to be in the right place at the right time to see things like Titan crossing Saturn's disk. But the other thing is that once you've missed that block, you've got to wait then about 13 years for the next slot. And there gets a point in your life where you start thinking, that's getting a little bit too far.
How many more of these?
How many more? Well, Halley's Comet is a classic, isn't it?
Yes.
Yeah. In 2090, there is a total eclipse of the sun which goes over where I used to live in Selsey.
Wow.
I'm quite upset about that.
Yeah.
Greenwich has been at the centre of important discoveries about time for centuries. I've come to meet Louise Devoy at the collection store to discuss a test masterminded by 9th Astronomer Royal Frank Watson Dyson that changed our understanding of time forever.
Hi, welcome.
Louise, it's lovely to be here in this fabulous place, and I think you've got something special to show us.
I do indeed, yeah. This is a plate from the 1919 eclipse expedition. So let's have a look on the light box.
So this is a photograph that's 100 years old, more than.
Pretty much, yeah.
I'm so glad you're handling that and I'm not.
Here we go.
Oh, that's beautiful.
It's really stunning, isn't it?
It's gorgeous.
At face value, it seems like an ordinary eclipse photo, but this is actually quite a moment of transition from Newtonian physics to Einsteinian physics.
In 1915, Einstein published his theory of general relativity. He proposed that if space and time were part of the same fabric, that fabric would be warped by any object with mass, producing the effect we know as gravity.
This was taken in Sobral in northern Brazil on the 29th of May 1919, and astronomers were really excited about this eclipse because
It was very long, about 6 minutes and 50 seconds, but also because it was going to be seen right in front of a star cluster, the Hyades and Taurus. So astronomers wanted to use this event as a way of testing general relativity. They wanted to try and measure a very slight shift in the position of the stars caused by the mass of the sun bending the starlight. There were 2 teams from Britain who went out, one from Cambridge and one from Greenwich, and they did indeed measure a deflection of about 1.75 arc seconds.
Which gives you, that's the value that Einstein's theory, not Newton's theory, predicts.
Exactly, exactly. I mean, it was literally just fractions of a millimetre on the plate, but really quite profound and significant.
Why was this such a big shift in thinking? What is it about relativity that makes it this sort of moment where it's before and after that changes everything?
So I think there's a mindset change in thinking about some of those fundamentals that we'd really taken for granted, like gravity and time, that actually they were a lot different to what we originally thought. So it must have been very unsettling.
That's right, in this sense beforehand that there are sort of fundamental measurements that you could all agree on. You have to throw that out for relativity. So suddenly you and I could be in different places in the universe and disagree about time. That feels crazy.
It does indeed.
It still feels crazy. Dyson's teams proved Einstein's theory correct. In the 21st century, it's now atomic timekeepers that allow us to test relativity at its limits. Pendulums replaced by atoms, ticking at over 9 billion oscillations per second. Modern tests of relativity often use instruments like atomic clocks.
Yeah, sure. I think one of the most famous ones dates back from 1971, the Hafele-Keating experiment, when cesium clocks were put on aircraft, just on like a commercial airliner, and sent eastwards and then westwards. And they found that there was a disparity between the clocks and a control clock down at the US Naval Observatory that really showed that sort of time dilation through kinetic motion. They also looked at gravitational time dilation as well. So if you're comparing clocks at altitude versus clocks on the ground, you can see that variation as well. So it's really incredible how you can detect those tiny, tiny changes.
Even fractions of microseconds are vital in our modern world. For financial transactions, for precision GPS, and even for spacecraft navigation. For a further test, there's now a clock in space to do this.
That's right. Even within the last few weeks or so, the European Space Agency has launched ACES, Atomic Clock Ensemble in Space.
Okay, good acronym.
Yeah.
Yep.
And then the idea is that that space clock can then sort of talk to other atomic clocks on Earth as well. So we can use that for science and also for applications such as position navigation systems.
Oh, I hadn't realised it was navigational as well. I'm interested in the science because you can do these subtle tests of whether Einstein was right, but this is a practical navigational thing as well.
Exactly. So we can use it to map the Earth in better detail. We can use it to potentially measure volcanoes, glaciers, maybe even earthquakes at some point. But it also has that application for the satellite navigation system. The better you know your time, the better you know your location.
I love this. We're in Greenwich and we're talking about putting clocks in space to do navigation and to study the Earth as well as physics. That's fabulous.
Great.
Einstein tells us that the way we experience time can be changed by our gravitational environment. This means that we may have some natural candidates for time machines in our universe.
So when people say to me, could time travel ever be possible? I'm like, well, technically now, if you were willing to get into a spacecraft that could fly, close to a black hole.
Close.
Close.
No. Okay.
Matthew McConaughey's done it.
Yeah, seen it done.
I mean, we've all seen Interstellar, right? I mean,
If you went close to a black hole, you would experience time passing normally for you, but compared to someone you left behind on Earth, less time would pass for you. So this could be a way to travel into the future.
Black holes aren't a new idea. The thought that dark objects could be lurking, undetected in our universe, intrigued scientists for centuries.
People have been thinking about black holes and the idea of a star so dense that it would collapse.
Dark stars.
Dark stars,
Yeah.
exactly, yes. Way back to, I think it was the 1700s.
Right.
Mathematically, we describe them as this unknowing singularity, where all the matter is crushed down into this infinitely dense and infinitely small point.
Yes.
That in Einstein's theory of general relativity, that point is undefinable in either space or time.
Yes. Because, for me, I've always thought of it as punching a hole in space and time.
Because it's more than just a dark star, a lump of matter that's squashed down to some size. It basically keeps on imploding more and more until it disappears. As you say, it punches a hole in space. That's a really nice way of describing it, because it has zero size, and that's what Einstein didn't like.
Yes, exactly.
It wasn't until 1971 that the first real black hole was detected.
Just at the start of the 70s is when Paul Murden and Louise Webster, who were hired by the Royal Observatory, Greenwich, to do their research, and they found a star that was moving on the sky, so much so that it must have been something incredibly heavy orbiting with it to get it to move and wobble around in that way.
Yeah.
That was Cygnus X1.
It was Cygnus X1, it was indeed, yes. It was the very first black hole that was ever been discovered.
What would happen to you, or me, if you fell into a black hole?
Oh, this is one of my favourite things to answer, because it involves my favourite word in the English language ever, which is spaghettification. Essentially, what would happen if you fell towards a black hole is that the gravity would be so much stronger. Say, if you were falling feet first towards a black hole, it'd be so much stronger at your feet than at your head, that you would get stretched out like spaghetti to the point where you'd be this long, thin chain of atoms, sort of on a
Doesn't
direct
sound
trajectory.
That sounds a bit painful.
But even if you do survive, weird, time and space get twisted around.
Yeah.
It's weird. I mean, is it the case that the direction you're heading towards the singularity at the centre of the black hole is no longer than a direction in space? It's now a direction in time.
Exactly.
Which is why you reaching the singularity is as inevitable as you reaching tomorrow.
Yes, and you can't stop tomorrow from coming, which is why everything ends up in the singularity once you cross that event horizon. There is literally no other path that you can take through time except to get to the singularity.
I'm trying to think what that means.
Don't try and visualize it, because it's one of those things that...
Hold a second.
We've had enough Prosecco for that.
We can talk about an infinitely small point in theory, but in the real world, it causes havoc with space and time. Chris is out to meet Professor Claudia Durand to discuss the solutions to this 100-year-old paradox.
So Claudia, in some sense, you've spent your career exploring the difficult bits of the universe in extreme conditions. Tell us a bit about what you work on.
So we understand gravity really so well, incredibly well, in the solar system, in the galaxy. But I like to think of gravity in the most extreme environments, so that can be in very small regions of space and time. So going down to 10 to the minus 33 centimeters, very small distances, where maybe the notion of space and time start making sense.
As we approach the infinitely small and infinitely dense singularity, we get to scales just 10 to the minus 33 centimeters across. That's a million, billion, billion, billionth of 1 centimeter. And it's here that our current understanding of space-time fails.
As you go enter the black hole and you go deeper and deeper into the gravitational well of the black hole, then the curvature of the way space and time are curled within one another is becoming so high that you can ask questions like, what happens when I take two particles and I collide them together? And the theory tells us that the outcome, it makes no sense. For instance, it may tell you that the probability of a particular outcome is more than 100%.
Right.
And then we know it's nonsense.
And what about the ideas that people have for going beyond relativity, of solving this problem that the theory breaks down?
Yes, we're reaching really the realm of quantum gravity. There's different alternatives out there. There's string theory, there's loop quantum gravity, there's causal set. And it is possible that something else has to come in. So string theory resolves that question by really saying that the fundamental constituents of matter, and in fact the fundamental constituents of all particles, including the ones that carry forces, they not point like particles, they are little strings. There's still a notion of space and time. It's just that the particles themselves, they are extended in nature. And so you can realize how this helps with having quantities which otherwise would be infinite because it's confined in one point, whereas in those strings it gets a little bit more diluted. It has an extent to it. And so that is a beautiful way to get rid of these discrepancies of what would happen at the center of the black hole.
So people have talked about maybe what happens if you go through this singularity as well.
Yeah. So you can think of mathematical solutions where you can connect the center of a black hole with a wormhole, for instance, or other dimensions.
What is a wormhole?
Let me imagine that if we're here, and I want to go to another point, so you're here, Chris, and someone else on the other side of the universe, an alien, is there, wants to talk to you, and typically it will take you a long time to go and talk.
You can only travel at the speed of light.
Unfortunately, yeah. So it may take you billions of years to get from one point to another, and maybe you don't have that amount of time. So instead, what you're going to say is, let me jump into a black hole. Good idea. So it's possible, and that's becoming more speculative, but this is space. This is space, and it's flat. And it will remain flat in here, but let's just imagine that as you go into the black hole in here, now you jumped into the black hole, space is so curved, and I can't draw it curved in here, but let's imagine it's so curved that you're enabled to connect that point here with a bridge, and let's call this bridge a wormhole, to another point in the universe in here.
So it's a shortcut, basically.
Then, exactly. Then it could be perceived as a shortcut using the curvature of space-time to connect different points in the universe together. And when you're at that stage, it doesn't really need to be even in our universe. You can go into extra dimensions if you want to.
And such things are allowed by relativity, right?
So,
you can solve the equations.
That's right. These are mathematically correct solutions, but physically, for this to happen, we need some kind of matter, we need some kind of framework which we don't think would be stable in the current stage. So it is very speculative.
Yeah. The astronomers here 350 years ago might be surprised by their successors spending time on such wild and wonderful concepts of reality. And yet today's science builds on their efforts to understand the cosmos. So that's why I'm not that bothered that we don't have answers to the biggest questions. What the Big Bang was, what to replace relativity with. Those will be solved by future generations. It's a team effort with each successive group of astronomers and thinkers contributing to the same cosmic story.
Back at the dinner table, the evening is progressing to the most important moment of any birthday party.
Oh, wow. Look at that.
It is a proper cake.
So good, yeah.
It sort of feels as if we should sing, but it might take a while.
And like 350 magic.
Do a test.
Let's raise a glass for
Yes.
350 years of the Royal Observatory, Greenwich.
Happy birthday.
Happy birthday,
Brendan. Yes.
The cake reminds me of another aspect of time that we haven't talked about. You can bake a cake. Well, I can't, but some people can.
One can.
One can. But you can't unbake a cake. It is strange that it's so natural to us that time should have a direction, that it only moves in one direction from past to the future. And yet in physics, all the laws of physics, all the equations of physics, we're told that time is symmetric. You can move forwards and backwards and the same things happen.
I wonder if it's our perception of time running that way. And could you leap out of that perception?
Well, that is, a lot of physicists and philosophers have argued that it's that time is really an illusion. It's just, you know, a construct. I don't believe that. I think the way we perceive time, it is what we say, it's objective. It's not subjective. It's not it's not just in our mind.
Head. Yes.
And this is still something after thousands, going all the way back to the ancient Greeks. This struggle to understand, does time flow? Why does it have a direction? What is now? I mean, that's the other, in relativity, right?
Define it, exactly.
Yeah. It's one of those really huge.
So it's relative, right?
Yeah,
To
there is
you,
no
the
now.
observer.
Yes.
Yeah.
Exactly.
Yeah, there is no moment now that divides the past from the future. Einstein says all times are equally real.
It's a very interesting thing to try and concentrate on this moment, this moment here, which is then gone.
Yeah.
And also, like, the current moment now is so hard to define because as I look at you, I'm seeing you as you were a few nanoseconds ago anyway. So what is now?
Yeah, there is
It's different for all of us.
It is a strange thing that we've grappled with for thousands of years and we haven't figured it out. Which reminds me, when it comes to time, it's time for me to leave because I have a train to catch. So I'm going to miss out on the cake.
We shall send you a piece.
Okay, see you all again soon. Bye-bye.
Sadly for Jim, we can't stop time, or his train from leaving the station without him. But for the rest of us, there's one final treat. The nature of light in the universe allows us to see stars and galaxies as they existed in their past. Just as astronomers have been doing here for 350 years, it's time to look up.
This is a fantastic piece of kit.
This is the Annie Maunder Astrographic Telescope. It is a 21st century telescope in a 19th century telescope dome, which is a bit of a quirk in itself.
So who was Annie Maunder?
She was one of very few women who actually had paid work at the observatory in the 19th century. So just in the 1890s, there was a bit of an experiment in having women as people who were doing the calculations.
So tonight, with a bit of clear up there, have you got anything in mind for us?
Yes, so this evening we are pointed directly towards Messier 13, which is the great Hercules globular cluster.
Yes.
And that is a nice bright target that people
Yes.
can find usually even with a pair of binoculars on a clear night.
It's a popular amateur target.
Yeah, and I think that was one that was discovered by Edmund Halley, who was second astronomer royal.
Yeah.
And there's a famous bit inside it, isn't there, called the propeller?
Yes,
Did
yes.
you pick the propeller up? Because I have a colleague that always denies it exists.
I don't think we can promise anything. Let's take a look. The light from the night sky is currently filtering through our telescope down towards a digital camera right in the end instead of an eyepiece. And then the image is being sent through this imaging software that you can see right here. And you can't see a lot. I mean, really what you're looking at is cloud, though something is beginning to peek through.
It was there earlier.
Yes, we saw it earlier.
Yes, me and Maggie have been keeping our eyes on this screen, this
Yes.
live view from the telescope, and we did see something.
Yes, and it went solid, but now there's a slight...
It started back.
It's teasing us.
Yes.
Yes, and it makes us practice the most important skill of astronomy in Britain, which is
Hope.
hope. Absolutely, and patience. Yes, but with clear skies and enough time to acquire the data and process the image, we get something that looks a little bit more like this.
Oh, wow.
One you made earlier.
Yes.
Yes,
But the
absolutely.
colour in the stars.
The stars contrast beautifully. And can you see the propeller? No, you're going
And
to
that is straight
Hidden
Ella.
away, yeah.
there. It's,
Okay,
it's
yes,
that dark
yes.
line, that one, and that one.
I see, yes,
I
the three
see it
planes.
now, yeah.
120 degrees apart, and that's what characterises that cluster.
It's been such a wonderful night. Good food and excellent conversation. Astronomers sharing their ideas about the universe, just as they've done at Flamsteed House for hundreds of years. Thank you so much for joining us. And from here, at the top of Greenwich Hill, good night.